Welcome to the debate. Today, we're digging into one of history's great engineering puzzles, Roman concrete. We look at structures like the Pantheon's dome. It's the world's biggest unreinforced concrete dome, still basically perfect after 2,000 years. And then you compare that to modern concrete structures that sometimes need serious work after just a few decades.
It's a pretty stark contrast, absolutely. And the source material we're looking at confirms that some of the mystery is finally being unraveled. These recent findings about hot mixing, and especially these lime clasts, acting as a kind of self-healing agent, it really changes the game and how we think about what they were doing.
Exactly. Which brings us to our central question for today. Does this incredible durability, this complex self-repairing chemistry we're now seeing, does it point to the Romans having, an advanced, intentional scientific understanding? Or was their genius more about really, really good empirical work, systematic observation, practical tweaks perfected over generations?
Right. It's about the nature of their genius, isn't it?
Yes. And I'll be arguing that the evidence now stacks up strongly for advanced, intentional design. I think they understood far more about the material science than we previously gave them credit for, something we're only now catching up to.
And I'll be taking the position that while their achievements were absolutely brilliant, undeniably systematic, it's better understood as the absolute peak of empirical practice, of standardization and refinement, rather than possessing the kind of theoretical, chemical knowledge we associate with modern science.
Okay, so let's start with the basics, the sheer longevity. We're talking about concrete lasting up to 2 millennia. That's potentially 40 times longer than many modern mixes. This isn't just, luck or a happy accident. It feels like proof of a really sophisticated design philosophy. They weren't just aiming for brute strength. They were engineering for stability, for endurance over vast timescales.
No one disputes the results. They're incredible.
Right. And this brings us to that key 2023 research. It really honed in on those lime clasts, those little white chunks everyone used to think were just signs of sloppy mixing, maybe leftover bits of unreacted lime. But it turns out, no, they were almost certainly created intentionally. The researchers figured out this hot mixing technique, basically, using quicklime directly in the mix. This generated really extreme temperatures almost instantly.
Which had practical benefits, for sure.
It did. And that's crucial. It had two major benefits working together. First, yes, the heat dramatically sped up the curing and setting times. You can imagine how vital that was for building something massive like the Pantheon dome quickly and efficiently. But second, and this is the mind-blowing part for me, this same hot process created these specific line clasts. And these clasts are like a built-in repair kit. If a tiny crack forms and water gets in, it reacts with the clast. It triggers this automatic molecular level self-healing. It recrystallizes as calcium carbonate and essentially seals the crack from the inside out. So you get speed and self-repair from the same process. That to me suggests deliberate optimization, a predictive grasp of how the material would behave over time. It points towards, a truly advanced material science.
I absolutely see the elegance of it, and the results speak for themselves. But I think we need to be cautious about projecting our 21st century chemical knowledge onto Roman engineers. Consider how we figured this out. This self-healing mechanism, the role of the clasts. It was only really understood in, 2023? And it took things like high-resolution multi-scale imaging, chemical mapping, basically incredibly advanced tools the Romans obviously didn't have.
Okay, fair point about the tools.
So what seems more likely? They clearly perfected a process. They had the recipe down pat, and it worked incredibly well. But the evidence suggests they probably landed on hot mixing primarily for its practical, logistical advantages. That intense heat meant faster setting. Think about it for an empire building on a massive scale. Roads, aqueducts, ports, all across the Mediterranean. Shaving off curing time is a huge deal. That immediate efficiency gain was likely the main driver for standardizing that technique. And if you look back at historical accounts, for centuries the prevailing wisdom, even among scholars studying Roman tech, was that the durability came almost entirely from the special volcanic ash, the Pulvis putillanus. The really complex role of these lime clasts, the self-healing bit, seems much more likely to have been a fantastic, but maybe unknown side effect of optimizing the mixing for speed and strength, rather than a deliberately engineered chemical feature they fully understood at the molecular level. They engineered the process, and the incredible longevity was perhaps a very fortunate outcome of that perfected practice.
I see why you'd emphasize the practicality of fast curing. It was undeniably a massive advantage for Roman construction schedules. But let me offer a slightly different read on those lime clasts. If they were just sort of accidental leftovers from mixing too fast, maybe an incomplete reaction, wouldn't you expect the results to be kind of variable? You know, some batches might have more, some less, depending on the conditions?
Possibly.
Yet, what the research shows is a remarkable consistency. We find these specific lime clasts with a consistent chemical signature, even though people used to dismiss them as flaws in structures spanning the entire Roman Empire, built over different periods. That consistency, to me, doesn't scream accident. It suggests a standardized, intentional execution of a process specifically designed to produce a material with these reactive inclusions. They weren't just aiming to build fast, they seem to have been designing structures with essentially a built-in immune system that could repair minor damage. You don't typically get that level of standardized beneficial flaw across an empire by chance. That points towards design intent.
That's an interesting framing, and I absolutely agree. The standardization itself is proof of incredible process control. That's where the Roman genius really shines, I think. Their ability to take what was likely a complex, high-heat chemical reaction and make it repeatable, reliable, producing superior results time after time, place after place. That is empirical mastery at its absolute zenith. But mastering the recipe, the ritual, even ensuring consistency, that doesn't automatically mean they possess the theoretical understanding of what we'd now call, nanoparticulate architecture. They couldn't see the atomic level scaffolding that made it work. The very fact that we are now trying to develop synthetic concretes based on analyzing Roman samples, well, it shows we're essentially rediscovering their successful result using our modern analytical tools.
They got there through meticulous practice, honed over generations, likely working backwards from what works best. We work forwards from theory. It's a different approach, even if the end product was revolutionary. Okay, let's push on this a bit. If the lime clasts were the intentionally designed star of the show, what about the volcanic ash, the Pozzuoli? The Romans clearly valued it immensely. They went to enormous trouble and expense to transport this specific ash from the Pozzuoli region across vast distances. They treated it like a strategic resource.
So they obviously knew it was crucial for durability. Right, they identified it as essential.
But the latest research indicates the ash works synergistically with the lime clasts. It often provides a sort of secondary, slower repair mechanism. It creates this denser, more stable matrix over time. So you have this multi-layered defense system. If hot mixing was adopted primarily for the quick cure, and the lime clasts were maybe this great side benefit giving immediate self-healing, was this deeper synergy, this second layer of long-term protection from the ash, also part of a grand chemical design? Or is it more likely the result of them finding a particularly good regional recipe near Naples, realizing it was superior, and then standardizing the use of that specific ash because their empirical tests showed it produced the best, most durable concrete?
I'm not quite convinced that the effort implies a lack of theoretical insight. Actually, I think it could argue the opposite. The sheer scale of the logistics, moving that specific volcanic ash, the pulvis putillanus, from very limited sources across the sea, across land, that enormous effort suggests they understood its contribution was fundamental, unique, and non-negotiable for the long-term chemical behavior they wanted. It wasn't just about how fast it set. Think about it. Roman concrete gets stronger over time. It shows this continuous chemical evolution over centuries. That's completely unlike modern Portland cement, which basically peaks in strength relatively early and then slowly degrades. For a material to actively form new mineral bonds and improve over hundreds, even thousands of years, well, that suggests they were intentionally engineering for chemical maturity, not just initial performance. They knew that specific ash was key to unlocking that enduring chemical stability. They weren't just designing a material to set fast, they were designing it to last. And you see this specialized understanding most clearly, I think, when you look at their marine concrete. Structures built in harbors submerged in harsh seawater for 2 millennia, think Caesarea Maritima, this stuff actually becomes more robust, denser, more rock-like because of its interaction with salt water. It actively uses the seawater chemistry to its advantage, forming resilient minerals like ettringphilite and tobermorite within the matrix.
Which is remarkable, yes.
It is, because modern engineers constantly battle the marine environment. Salt water aggressively attacks standard concrete and crucially causes rapid corrosion of the steel rebar inside, which is the primary failure mechanism for modern marine structures. The Romans, by creating a material that didn't need steel reinforcement and actually thrived in salt water through continuous internal chemical repair, well, that demonstrates an incredibly advanced design perspective. They specifically optimized the material for one of the toughest environments imaginable. That level of targeted specialization really pushes back against the idea of it being just a fortunate accident or simply finding the right local dirt. It points strongly towards designing for a specific, challenging purpose.
Okay, the marine concrete example is definitely compelling. It does make the happy accident argument much weaker. I'll grant you that. It shows a level of specific tuning that's hard to ignore. But here's the counter question then. If their understanding of this complex chemical evolution, this self-healing, this environmental optimization was so profound, if it was truly codified science as we understand it, why did this absolutely revolutionary knowledge just vanish after the Western Roman Empire collapsed?
A fair question. The loss is tragic.
It is. The systematic understanding of hot mixing, the appreciation for the lime clasts, the synergy with pozzolana, it just disappeared for over 1,000 years. Construction reverted to much simpler, weaker lime mortars. If the underlying science was truly understood and written down in theoretical terms, you'd expect it to have survived somewhere, maybe in Byzantium, maybe copied in monasteries, anywhere knowledge was preserved. But it seems like it didn't. The knowledge appears to have been deeply embedded in the practice, in the highly skilled craftspeople, the engineers on the ground who knew the recipe, the ritual that worked. And that kind of practical, embodied knowledge is inherently fragile. When the trade networks break down, when the large-scale imperial projects stop, when the specialized workforce disperses, that knowledge gets lost easily.
The fact that it vanished so completely suggests that the theoretical underpinning, the transferable scientific principles, as we define them, might have been the missing piece. They knew how, but maybe not fully why, in a way that could be easily written down and passed on abstractly.
The loss of knowledge throughout history is, as you say, a profound tragedy, especially with something this impactful. But I don't think the loss of a technology necessarily negates the sophistication of the original achievement itself. We know from Vitruvius, from other surviving fragments, and critically from the structures themselves, that Roman engineers were meticulous planners and recorders. Look at how they completely designed around the problem of steel corrosion, the main thing that limits the lifespan of modern concrete. They avoid it entirely by relying on the concrete's own internal chemistry for longevity. That feels like a significant intellectual leap, focusing on material science solutions for durability, where we still heavily rely on mechanical reinforcement, the rebar, which ironically becomes the structure's Achilles heel over time. They were thinking about permanence in a way that transcended the typical lifespan of empires, let alone buildings. That implies a deep, intentional design philosophy.
And yet, we circle back to the how. They were undeniably masters of the recipe, the process control, the standardization. Their engineering manuals, their legions of builders, ensured they could replicate success across vast territories. That's brilliant engineering, no question. But maybe the truth is often found not just in the final product, but in the path taken to get there. And their path seems to have been one of systematic, empirical optimization, relentlessly testing, observing, tweaking mixtures under real-world conditions until they landed on formulations that performed exceptionally well, especially under stress, leading eventually to this amazing self-healing material. It reads like the ultimate triumph of systematic trial, error, and refinement, rather than necessarily deriving it all from first principles of theoretical chemistry.
I still maintain that the sheer complexity and integration of the properties they achieved, the rapid setting combines with continuous self-healing, the tailored environmental resistance, the avoidance of built-in failure modes like corrosion, all stemming from that hot mixing process and the resulting lime clasts, it strongly supports the view that Roman builders had a sophisticated, intentional grasp of material science. Their approach, prioritizing long-term chemical stability, perhaps even over initial compressive strength, was arguably more advanced in certain respects than our own focus today. They were literally designing structures intended to endure for millennia.
I completely agree on the brilliance, the systematic approach, and the unmatched results. Roman engineering was phenomenal, but I still frame it as the absolute pinnacle of empirical achievement, observation, standardization, refinement, and practice. They perfected the recipe through rigorous testing and application, achieving results that relied on complex chemistry. But whether they fully understood that chemistry down to the molecular interactions of clasts and pozzolans in the way we can map it today, I think that remains the crucial distinction. It was a spectacular recipe executed with unparalleled skill and discipline across an empire.
You know, perhaps the most insightful takeaway here isn't about choosing one side definitively. Maybe the truth really lies in a fusion of both perspectives. It was clearly a revolutionary, systematic approach. It was undoubtedly empirical in its development and refinement over generations, but it also seems to have possessed a depth of design sophistication, particularly regarding material chemistry and longevity, that we're only now, with all our modern tools, beginning to fully grasp and appreciate.
I think that's a very fair assessment. It's rarely either or, is it? And the story of Roman concrete definitely challenges that simple idea of technology always marching forward in a straight line. The fact that knowledge this valuable, this effective, self-healing concrete could be utterly lost for over 1,000 years is, well, it's humbling. It confirms just how fragile practical expertise can be, especially when it's embedded in specialized traditions rather than widely documented theory. The Pantheon isn't just a monument to Roman engineering prowess, it's also a pretty profound reminder that sometimes ancient wisdom really did hold secrets we're still working to rediscover.